So your graph should look like this for number one, right? Guys, quiet, please. Thank you. Quiet. Stella. Thanks. Okay, sorry. Sorry. Graph should look like that. Very simple. Asymptote y equals 0. There. Very simple again. Asymptote y equals 0 again. 3. Very simple. But you got to move 2 to the left. So the parent function, I think, is shown in pink. Bless you. The transform function is in blue. Or is that right? Wait. Yeah. Okay. That's just sorry. I was just throwing off a little bit here. Yeah. The transform function is one in blue. So the range should actually be yeah. The range is still fine. Again, the pink is parent. The blue is transformed. 4 is only one transformation going 2 up. So you can see the blue function went 2 up from the pink. Changes the range in the horizontal asymptote. And then 5 is kind of weird, but negative 4 to the x is actually the parent function. Now, technically, it's negative 1 times 4 to the x. The negative 4 is not the base. The base is 4, but negative 1 is the reflection. Kyle, go ahead. No, so y equals 2 because we went up 2 units. Exactly, 100%. Right. The vertical shift causes the force asymptote to move up or down. Right. Yeah, for 5, you're going 1 left compared to the parent function. So, and this is flipped over the x-axis because you have a negative out in front. So hopefully we're good at that. Cool. All right. All right, that's easy. Today's notes will be easy as well. Well, kind of. There are 4 pages here. Okay, the notes afterwards I think are shorter. That's okay. That's all for later in the week and next week. Okay, well, let's get moving here. Oh, the homework is short. I think that's what I meant to say. Okay. Okay, exponential modeling. It's actually one of my favorite things to do. I love this stuff. All right. And we're recording still, right? Yeah, cool. Okay. So let's look at exponential population modeling. So an exponential function, as you guys know, is y equals a times b to the x power, right? But what we could do is think of b as 1 plus r. What do you think r represents? Just think into rate, exactly. It can be the rate of growth or rate of decay, depending on what you're considering. So if a population is growing, of course, it's the growth rate. If it's losing population, it's the decay rate. And we usually do it per year. So t is usually done in years. What do you think p sub 0 for the subscript with p and 0? What do you think that represents? Initial, yeah. What you initially start with. And then p of t, what do you think that represents? This is the function notation. So this is actually just like one variable or one quantity. What do you think that represents? P of t. Is that like it added at the time? Yeah, the population has a certain period of time. Like after 10 years, what would the population be, or 20 years, whatever t is, right? And of course, if your r is positive, because your base is bigger than 1, you're going to grow. Exponential is going to grow. If the base, sorry, if r is less than 0, that should be intuitive. It's a negative rate. Then of course it's going to decay. It's going to be going down. So that's what's happening there. So let's look at this case. Let's say the enrollment of Sacred Heart Prep grows 3% every year. And right now the current student population is 5. I know it's more than that, but say it's 550. So then right now you have 550 people, right? But after 1 year, how many people do we have now? You have that, which I foolishly left my calculator in my classroom. That's okay. I can pull up one on my device. Give me a sec. Is there a calculator in this room? No, that's okay. It's all right. I'll just do this so everyone can see. So you can just do this, 550 plus 550 times 0.03. Does that make sense? Because you're adding 3% of 550 to 550. So you have 5, we'll say 567, we'll round up. Because you can't do half a human being, it's kind of weird. Then you're doing the same thing. We're doing 0.03 squared, then multiply by 550, or 0.03 cubed, times 550. And what you could do is you could just repeat it, but raise that to the second power. Whoa, what did I just do? Oh, okay. I'm glad I did this, actually. I didn't mean to make this mistake. I'm actually glad I did.
You guys what I did wrong for the second line? Well, it should be getting a bigger number, right? Intuitively. Was that good? Yes, I didn't follow order of operations. I went against my own words. I always
Preach you guys order of operations. So I should have done, because I wanted the change to be squared, right? The change is not 0.03. The change is actually 550 times 0.03. That was my mistake. I'm glad I did that. Okay, much better now. And that's kind of, wait, does that make sense? Hold on. Wait, what am I doing wrong? Well, I'm doing something wrong here, guys. Oh, darn it. Okay, I'm doing another mistake again. Okay, let's back up a little bit here. Yeah, okay, let's back up here, guys. I'm really screwing up royally today. All right. Yeah, I have to do 567 plus 0.03 times 567. There we go. My apologies. It's been a long day. Okay. That was a fundamental flaw, total flaw on my part. What I should have done is this. Let's back up a little bit. So 550 plus 550 times 0.03. Okay. Then plus that number times 0.03, because now that's an increase by 3%. Now I feel better. We'll say 583. And then 583. So you're always taking the percentage of the previous problem, right? Or the previous output. So plus there we go, about 601 students. But if you think about it, this is not a terribly efficient way of calculating the change, right? What if I say, like, what's the population 10 years from now? So I got to do this like 7 more times? No, don't do that. You would just do this, 550 times 1.03 raised to the t power. That's what you do. That would be a more efficient way to do it.
think about it. For the first problem here, you factor 550, you get 1 plus 3. The 1.3 is going to risen to that over. That's what's supposed to be happening.
Okay. So now here, while the following population models exponential growth or decay was a percent rate of change. Well, because your b is less than 1, that's decay. Because your b is bigger than 1, that's growth. Here, the percent change, you do 1 minus 0.9976, which is 0.0024, I think, or a 0.24% drop. Here, that's a we do 1.0030 minus 1, 0.003, or a 0.3% increase. And the reason why is that each time, that's 1 plus r. So I'm setting these each equal to 1 plus r and solving for r. When I did it for part A, I moved 1 over, or I set equal to 0.9976. Technically speaking, actually should be a negative number, but it's okay. We know it's a drop. Part B makes sense. If I set equal to 1 plus r to 1.03, solve for r, I get 0.03. Now, just as a fun social problem, why do you think abstinence decreasing and why do you think mental parts increasing?
Let's back down an applicant. So why do you think Athens have a decreased population?
It's expensive. Also, probably people bought their homes maybe 40, 50 years ago. They're probably pretty old. probably died. They probably didn't move out of their house. And parents probably, I mean, so kids probably sold and made lots of money. Actually, it happened to Sacred Heart educated her husband bought a house. She died last year, but she retired in 2012, and her sister, I mean, so her daughter, I think, made like $6 million on the sale of the house, but only for 100,000 in 1970. Right. So that's pretty. Yeah. So I think a lot of people can't afford. Yeah, it's expensive. Menlo Park. People might buy Menlo Park because Menlo Park is probably a little more family focused, right? It's got parks and whatnot. I don't know. It's still expensive, but yeah. Anyway, it's kind of a fun problem. Okay, Redwood City. That was a big address. Well, I think that's a big address. It's cheaper to buy in Redwood City, right? Redwood City, even though you still need $2-3 million to buy a house in Redwood City, still not cheap. Let's look at example 2. So let's say we start at that many people, sorry, poor grammar. Oh, decreases. That's interesting. Okay. Oh, I thought it was gonna be increasing. Okay, well, we'll go decrease. So be it. So if you do a population model, you can write it like this. Or if you want, I don't really care if you do this also. Either way is fine with me. But if I'm gonna be a little more formal, I'll go the one on the left side. So the population will be 73,114 people. But now I'm going to subtract. It's going to be 1 minus 0.0303 raised to the 5th power. And we just have to work that out. I don't believe that. I'm pretty sure Rose is grown, but I'll go with what the problem says. 1 minus 0.0303 raised to the 5th power. So it looks like it's about 62,688 people. Okay. That's good. So again, we see the same formula again, but now we're dealing with compounding interest. You guys may have done this last year in Algebra 2, I think. So the amount of money after 2 years of investment interest is added once at the end of each year. We really just say it's like this. Sometimes we say A equals P and actually in general, let me back up a little bit here. So P actually stands for principal, which is your initial amount. T, of course, is time in years. R is your interest rate. So it's going to be a decimal. Because if you say 5%, you write as 0.05. And K is the number of times your money is compounded per year. What that means, compounded, means how many times interest is added to your account. So if you put your money in a bank or some sort of account, if it's compounded monthly, that means the bank will actually see how much money you got, and they'll update it monthly. So it's basically how often your money is updated. Like this daily, your money is updated daily, weekly. Or quarterly, every quarter, like every 3 months, it's updated. But what you have to do then is you have to spread out the interest rate over that time frame. So like, for example, credit cards have like the highest interest rates are absolutely crazy. That's where actually you pay money. You don't get money. They get money from you. So if you rack up, say, $10,000 credit card debt, that's a 27% APR, which is totally ridiculous. They usually they bill you every month. So they update the account every month. And so then they take, 27%, but divide it by 12, and they add it on to the account. And then all of a sudden your balance is now $5,200. Oh, crap. Now I have more money because I'm paying all this money interest. So very important. Or sorry, $10,200 if it's $10,000 credit limit, but whatever. But be careful with the credit card. It's very important. So let's look at this one here. But what if a bank gives you an APR annual percentage rate, but gives you the interest at the end of each quarter? How would you adjust the formula above? I just showed you right now how to do that. I just did it for you guys right now. It was just P 1 plus r over k, kt. I call the k the, some people use n, I use k. You use any letter you want for the compounding. So how would you just the formula if it was monthly? Sorry, let me show you what I'd do for this one. We 1 plus r over 4, 4t. This would be p 1 plus r over 12, 12t. A equals p 1 plus r over 365. We won't assume a leap year. And so daily looks really nice, right?
Like, wow, I made money every day. But the rate is like such a trade-off, right? Yes, this will be a little bit more money than monthly or quarterly, but it's not that much difference as you find to work it out. Yes, you raise it to a bigger exponent, but the base itself gets smaller. So it's a trade-off between the two.
Does that make sense? Yes, that's the formula there. Now, and again, it's kind of very repetitive. Again, it's the same thing. So let's work out a problem. You start at 500 bucks, 7%, 10 years, quarterly. So you're given 4 pieces of information. You're given the principal, you're given the rate, you're given the time, and you're given K. How many times you're updating the account every year? Every year you're updating it 4 times. So how much money do you got? $500. 1 plus 0.07 over 4, and 4 times 10. And you just plug and chug. So this is assuming you put $500 in an account and you don't touch it for 10 years. You check 10 years later how much money you got. You should have some money, I mean, should be okay. You really should be putting money in every year or every month or so just to keep the money growing, but that's all right. Yeah, so you get about $1,000, $1,000.80. Okay. So we're good there? Okay. All right. Let's keep on moving. Now, continuously, so let's think about it. Here's our formula again. $1,000. 1 plus the interest rate is 8%. K. And you're doing it only for 1 year. So you just have K up top. Okay. So here K equals 1. Here K equals 4. Here K equals 12. Here K equals 365. How many minutes in an hour? And then how many hours in a day? So you gotta do 24 times 60 and then times 365. Yeah. That's I think from the movie Rent or the play. So anyway, yeah, 525,600. Okay. Okay. Yeah, that came out like many years. I think when I first started teaching, it came out like a lot of my students would start singing it. All right. Okay. So what I could do to make my life a little more manageable for this problem, and this is actually very good for you guys to see, because I could do this computation 5 separate times, but I think you guys might appreciate this a bit more. If I go to y equals and actually punch in the equation 1,000, and this all records, so you can watch this at a later time, 1 plus 0.08 divided by x raised to the x power. So what I've done is I've stored the equation under y1. I'm going to go back to the home screen, hit alpha trace. You can call up the equation and plug in 1. So $1,080. Then what I'm going to do, if I hit second enter, it repeats the equation. of the foreign. So what you're doing, you're treating this like f of x notation. That is what you're doing. You're making this like f of x notation. Alpha trace is how you do it.
Over this, aren't you just supposed to just write the equations? That's what this problem is asking.
I want to find the answers. I'm solving. So yes, I mean, yes, I know we're supposed to write the equation, but I want to solve it actually. So 12. So you see it slowly increasing. Exactly. Right. Exactly. 100%. I know the athletes have to leave in about 10 minutes, so it should be done very soon. And that's $1,083 per round. But do 365. Goes up, I mean, whoop-de-doo, like 27 cents, right? Or 28 cents. Now, interestingly, this gets really, really interesting, right? How much did I gain?
Because daily to, I mean, minutes, I mean, daily fine, but tomorrow fine, you know, they don't count, that's it, don't count, but minute, like, okay, 207, okay, 208, I'm gonna get a little bit more money, 209, get more money, 210, get more money. But how much more money did I really make? An extra penny? To go from that many times I'm counting, so fine, so banks are update my account 365 times in 1 year. Now the bank's gonna update my account 525,600 times, that sounds crazy, but I only gained a cent, right? Only gained a cent.
What this tells me is that there's a limiting case, that ultimately we reach a limit. And how do I reach that limit? This is something you guys have seen before. I think we did in algebra 2. I don't remember, but it's a number E. Are you guys familiar with the number E? Yeah, so the number E is roughly 2.718. And where does it come from? It comes from this. That's where it comes from.
So it's 1 plus 1 over x raised to x. So it's kind of similar here. I put it away, it says 1 on top here. But it's very, very similar. This expression converges towards 2.718.
So ultimately, there's going to be a limiting case after a while. And what you could do is the formula could change, and the formula will look like this now. Yeah, second ln. It's on the left side of the, if you have a TI-4 calculator. So it's second ln. That's how you look at E. So if I did 1,000 times E 0.08, it converges to that. I should get 1,083 and 29 cents. So if I go back to my calculator again, times second ln. Yeah, so it just converges. So that's compounding interest. Now, where this stuff gets really interesting, I don't know if we'll go down this path. I'm actually going to try to make a case that we do talk about this. It gets really interesting. You start talking about future and present value. Like, for example, if you buy a house, what happens if you buy a house in the Bay Area for 20 years? It's going to go up. It's going to go up. Or what if you owned a house here for about 20 years? You probably made a lot of money, right? As I explained, like, actually, I think it was Wisteria, Atherton, home sale. Yeah, there it is. So this is a Sacred Heart teacher. She taught world civilization. She retired in 2012. She died last year. She was 90 years old. Actually, Dr. Wickham had her as a teacher, and she was actually a close family friend of ours. So she bought, when did she buy this house? It was built in 1953. Hold on. I swear it's right here. Did I miss it? No, sold for that much, but what was worth? What they paid for it? Well, anyway, I know they only paid $100,000 for it and sold for $5.7 million. So That's future value. That's a different kind of formula you'd use. Or if you take a loan out, that's present value, how much a loan is worth if you make, or how much it goes down. Let's see if we have time to get to those formulas. Those are really cool formulas.
Wait,
Charlie?
what are you looking at right now, the 2002? What is that?
That is actually what the county assessed the value to be.
So
because
2000, those were.
well, it's just what they figured. No, it was actually worth probably more.
Yeah.
But because it's retroactive to when you bought the house, so you pay the property tax on the old value which you bought. So if you bought the house in 1970, they assess the property tax based. Because your property tax is it's about 1% of the value of your house, but what you paid for it. So now someone paid $6 million for this house. Now they're paying $600,000 in property tax, or something crazy, something astronomical like that, or sorry, more like $6 million. So anyway, it's all this kind of neat stuff. I always kind of like this stuff. Anyway, let's keep moving, guys, so I don't get sidetracked here. So let's work this out. Mike invests that much money, compound continuously, so you do this. And whatever that is, yep. So that's that one. Pretty simple. And then one more. Which one's a better investment? $8,000 for 6 years. Sorry, you're investing $8,000 for 6 years. Should you do 7% per year compound monthly, or a smaller percentage rate but compound continuously? Which one's a better investment? So if you do 8,000, 1 plus 0.07 divided by 12, 12 times 6, or 8,000 times E, 0.0685 raised to the 6th power. And gosh, wish I had a handheld calculator on me. It's fine. So 8,000. Or 0.0685. So actually the first one's better. And that's this one over here. So that's a better investment. So anyway, very straightforward stuff, not that hard. Homework, you have some time. We did get out, what, 2:40, I think? Oh, 2:35, got it. So yeah, homework's right here. You already have the homework package, so feel free to work on it. We have those steps here if you need brain breaks, totally fine. Good luck to the athletes today. The answer keys, all the answer keys are created. I'm gonna upload a bunch of stuff to schools right now, so you guys have it, and we're all done.